what I'm going to do is just briefly go through some of the things that we came up with in the Foresight review of robotics and autonomous systems. And there's a bunch of people who've been involved in that. But Ruth suggested, why not do something a little bit lighter to start with, just to emphasize what's going on in the area generally first, so that to earlier points, and perhaps stimulate your interest to go and look at the review. It's an area that's receiving a lot of interest worldwide at the moment. The language or the narrative is, in the same way that computers revolutionized everything that uses data. Robots and autonomous systems are revolutionizing everything that moves. And if you think about what moves, it's a lot of stuff, right? So there's a big impact going on. And it's happening in lots of different sectors, and it's happening all over the world. And there are lots of reasons for it, to do with computing power increasing, to do with people getting smarter at doing algorithms that can make robots do clever things, be smarter, and to do with reasons of productivity. But what was nice about doing this little piece of work for Lloyd's was because we looked at it through a very different lens, which is the lens of the Foundation's charitable purpose around the preservation of life and infrastructure. And I'll come back to more of that later. So just to dance through a few examples, I'm going to cut some of this stuff out to keep it. Can we switch the sound off, please? Thanks, that's great. Just to show through some examples, by the happenstance of cut and paste from another presentation, these are all British examples, but I'm conscious that Lloyd's is a very international organization, so don't read anything into that. But here's a great example of a robot and an autonomous system. It's Dyson's new vacuum cleaner. It has that thing on at the top there, which is its 360i camera system, which it uses to navigate and to map your room so that it can hoover it or vacuum it successfully. If you talk to Sir James Dyson about this, he always jokes about what they're doing with all the data they gather from the vacuum cleaner back at Dyson HQ. And you might care to think about that if you choose to buy one and use it in your house. Driverless cars are big. There's a set of trials going on at the moment in Milton Keynes. And Ruth again was kind enough to point out to me that in the news last week, it was announced that they were being successful and they were avoiding both a dog and somebody playing Pokemon Go, that's right. So one of the issues is with driverless cars, how well can they sense their environment and avoid? And certainly there's more trials going on later this summer winter in Greenwich. So living lab type stuff. So these are coming. OC Robotics, British company producing snake arms that are being used for inspection, and a lot of the kinds of integrity management and asset integrity solutions that require inspection use this kind of technology. And we're getting better at it, and we're making it cheaper and making it more affordable and less power hungry. This is an Edinburgh-based company, Touch Bionics, and they're doing prosthetic devices, most notably hands here, and this is one of their latest ones, the iHand. It has some intelligence, some smarts inside the hand, so it's very difficult to build good sensor connections to your muscles, and so therefore to have the hand understand what you're asking it to do. So therefore, with very simple connections to your nerve, not directly to your nervous system, but through your skin, you have to be able to produce a series of different behaviors from the hand in order that it does different operations. And Touch Bionics have got one of the most successful examples of that. This is a consequential robotics product, so I should be careful what I say. It's IntelliTable. So sometimes the robotics revolution is revolutionizing things that don't move into things that do. And this is an example of a sort of assisted living in a care home environment, and the next generation of this will have a small manipulator on it so it can actually pick things up and do things. And companion robots are becoming popular. We anthropomorphize our robots unbelievably, and there are legion tales of things that people do. Miro is just electronics and software, right? But isn't he cute, right? And there's a big market for this, right? Digital pets, it's just too much hassle having a real dog, right? Because watch this space for Miro. the things that distinguishes all these kind of systems is how do you interact with them. And one of the language is autonomy is all about the operator. That sounds strange, right? So we talk about manual control teleoperation, we talk about shared autonomy, and we talk about persistent autonomy. And I'll try and just indicate what I mean by that. Here's one of our, I can't resist showing off one of our new toys in the Center for Robotics. It's Valkyrie. It's a NASA humanoid. There's quite a lot of research going on in humanoids at the moment to understand, well, actually, seriously, it's because it's fun, I think, is the real reason. And that drives a lot of creativity. But there are serious engineering challenges behind that about control of balance, controlling multiple things at the same time, force in contact and compliance, motion, velocity, balance of the whole body, and machine learning techniques and artificial intelligence are proving to be one of the ways that this is being done successfully. And that's an example. That's an example of shared autonomy because the operator is telling the robot what to do, but the robot has enough control software on it and sensing software that it can understand for itself. This is an example, commercial example of persistent autonomy. So here, this is a thing called the Autonomous Inspection Vehicle. It's a Subsea 7 vehicle. It's being used now for commercial work in the North Sea for Shell, doing inspection around floating production systems is the target market. And so it carries sonars, it carries videos. It's completely autonomous. It has no physical connection to the surface. And because radio waves don't propagate underwater, you can't really communicate with it other than through get heartbeat information about what it's doing and maybe the odd JPEG snippet from one of the vision sensors. So this system works autonomously. It has a map of the oil field in its brain, and it navigates its way around the oil field. It has a mission plan, which it can adapt to some extent on the fly, or I should say in real time, in order to carry out the inspection mission. So this is quite advanced, and in fact, some of the most advanced examples of autonomous systems are in the ocean because of these physical properties. And I'm going to skip through this because time is going to get out in the way. I want to talk about this one a little bit, though. This is actually a live demonstration from it's not from our, although we have this robot and we do some of this stuff, this is actually a different group from the Technical University of Munich. It was at a live demonstration they were doing at Automatica, which is an industrial robotics fair a couple of years ago. And it's PR2, and it's the robot. It's got sensors. You can see the laser scanning away there. And it's got stereo vision system to connect. So it's mapping the kitchen in front of it, and it's making popcorn. The reason this is interesting and significant, apart from all the sort of mapping and control and where is everything, is that in order to understand how to make popcorn, this robot went off to the internet. It went off to WikiHow. It downloaded the recipe for popcorn from WikiHow, and then figured out for itself all the intermediate planning stages it had to do in order to make popcorn, which is, figure out where is the pot, do I have to open the drawer to get the pot out of the drawer, and then what are the sequence of actions I actually have to do. And there's a lot of intermediate stuff that's not written down in the recipe for popcorn that it has to figure out. These the future of robotics, I think, is going to be increasingly that the hardware, the robot, becomes a commodity. And it becomes like your smartphone. On your smartphone, what it does for you is a function of the apps that it has on it. So you download the apps which make it do stuff that you like, that you want. And it'll be the same with your robots in the future. You'll download the knowledge, how to make popcorn, that gets the robot to do the things that you want it to do, to plan for itself. And you download the control algorithms and the sensor processing that you need. And it'll be invisible to you, but it comes from the connected, and it comes from the cloud. And so one of the driving features in all this is where does knowledge come from, where does data come from that give the robots the capability they need. And just to continue on where's the boundary at the moment? Here we are trying to teach the robot how to turn a valve in the maritime environment again. So what the operator is doing on the left there is he's controlling the robot directly, and we do 2 or 3 runs, swimming up to the valve panel, turning the valve, and the robot learns it. But what it learns is essentially a load of probabilities. It doesn't learn the sequence of movements or anything like that. It's probabilities. It's a Markov process, if you're into that kind of thing. And that's a very powerful way of teaching robots behaviors that they can then go and do things later on. And we've applied that to lots of other things. Here we are cleaning an anchor chain, and it's having to deal with all the the dynamics of motion, of the reaction forces on the robot and the uncertainty that comes from that, and also some error detection and recovery as well, which I haven't got time to talk about here. And if you want to, there's a typo there. If you want to know more about this, a quick plug, we're organizing next March the European Robotics Forum in Edinburgh, 2017. There'll be 700 of Europe's best roboticists from industry and academia coming along. Do come and join us if you can. So to the Foresight review, and I'm grateful actually to Ruth for pigeonholing me and suggesting, would we like to put a team together to do it, because it's been enormous fun. It's been quite hard work, I have to say, and that was unexpected. And it's been a review which has, in the final document, largely been written at 2 o'clock in the morning. And the reason is that the team that we assembled to do this are hugely talented people, but also hugely busy people, and the only time they can generally get to do it. So it's been a bit of a labour of love getting it out of the door, but we got there in the end, and that's good. And the point I've made just now about doing it through Lloyd's Register Foundation's charitable purpose, I've already made that. So it's a different lens, actually, and that stretched us because we weren't used to thinking about that, and we had to get out of the mode of thinking about jobs and growth. Here are some of the characters that were the principal authors, and I have to acknowledge David Bissett, who's sitting over here. David's been one of the heavy lifters in getting this over the line, and I'm very grateful, and he should get great recognition for this. Most of these people are engineers or come from a research and engineering background, so that was the core team, because we've done stuff a bit like this before, and we thought this is the right team. But what we recognized is the narrative about robotics autonomous systems is not just coming from people from the sort of research, engineering, industrial community. There are a lot of other communities thinking about it from the point of view of law, from the point of view of economics, from the point of view of ethics, sociology, jobs, public policy, and so on. And so what we really wanted to do in the workshop that we ran, and you can't read this, so that's good news, is put together an international team, but also an international team that's quite multidisciplinary, just to see where it went, because the nature of the exam question is about, how can robotics and autonomous systems, what are the white spaces in developing robotics and autonomous systems that can support preservation of life, preservation of infrastructure. And the engineers aren't the ones who are going to answer all those questions. So we put together this group here, and we had representatives from all those, and it was very interesting. And one of the things that I learned from it was, and it was a very honest comment from one of the sociologists stroke economists, a person who's written extensively on the subject of robotics and jobs, who's been influential in influencing the narrative that comes out in the media. And she said, it's the first time I've ever sat down with engineers and scientists who do this to really understand what's going on. Right? And so that was a huge connection to make between these different communities. And it made us appreciate the extent to which you need this multidisciplinary look at it in order to get the right perspective and the right solutions to the answers. Are you going to change? You are. So we started off with some definitions of what is a robot. That's the hardest bit, right? And we came up with the arms, legs, and sensors of big data working in the Internet of Things. And here's our little Mickey Mouse, looks a bit like Mickey Mouse with the ears diagram, to get that across. So, and they're very connected. And you'll find that people who are thinking about big data, AI, a lot of that smart stuff is actually what empowers the robot. The difference is it works in the real world. I heard a lovely story. Actually, it's in The Guardian today, I think, or yesterday. There's a poor chap who bought himself a wireless-enabled kettle in the Internet of Things. It took him 11 hours to make a cup of tea. He hadn't got the right drivers to get the Wi-Fi up and running. And it went viral on Twitter. Yeah. And so do watch out for that. There's a series of great comments about, I can't get... So it was a salutary lesson, actually, and one I take. But the key thing about robots that for us that define them is that they have some kind of extra smart processing software on them. It's not just the sort of industrial robot that you'll see in a car manufacturing plant, which blindly does what it's been programmed to do. These are devices that have some active sensing. They can do the sort of stuff that you saw in the videos. They're more advanced in control. They can sense their environment. They can make decisions. They can adapt. And that's the key thing that distinguishes this new generations of software and robots. And it's actually all about the software. Right? It's the software that makes what the oil and gas industry taught me to call it, make dumb iron smart. Right? Because most of the stuff in the oil and gas industry previous to that was. And there's a bunch of different things they're doing, gathering data, transporting things, manipulating things, and doing sorting and storage. We sat and thought a little bit about what are the ways that robots can improve safety, and we came up with a long list about, replacing the worker so the worker isn't in harm anymore, supporting the worker. I think one of the things that we're very keen to get across actually is that the robots aren't things that replace people. They're things that support people and complement people, give them more time to do the things that they're good at, quite often cognitive tasks, but not always, or interaction tasks. And they're not uniquely devices that replace people and therefore replace jobs. And I know that's not the Lloyd's piece, but it's very important. I think it's very important to put across. So they actively collaborate with people. There's lots of activities around doing inspections of assets and infrastructures. They can go into places where people can't. If the building's collapsed, you can send the robot in there. You can drill with a robot. You can't drill with a person. And safety critical operations, the robot can have some role in some of the assuring of the products that are produced, or if it's a manufacturing thing. And we also were keen to get across the difference between a robot and an autonomous system. And we included autonomous systems in this deliberately because there are examples of this kind of smart software that don't control physical things. So in the financial industry, for example, this very fast trading that goes on, in milliseconds or fractions of a millisecond, those are autonomous systems that are doing that. They don't have a connection in the real world. It's all data basically, but it's the same thing that's going on behind the scenes. So we included that in our definition. And you can't see this very well. The colors haven't come out. We spend a lot of time thinking about data, and curiously, if you look across the report, actually a lot of it is about data and knowledge. It's not just the robot. It's the physicality of the robot. It's the data and the knowledge that become some of the issues and some of the areas that we think the future is that we have to focus on when we get to the recommendations part. But thinking about where data comes, where data goes, what you can do with data, it comes from the asset, whatever the device is. It comes from the inspection robots that go on around it. Drones are... I didn't have an example of them, but they're everywhere, and they're probably one of the most prevalent new kind of inspection device that everybody's using at the moment. But you find that the data that you gather for the class of asset, so the kind of oil rig that you're looking at, or whatever the system is, or building, or railway, you'll find that sharing that information across different examples of the same asset is actually quite a powerful thing to be able to do to help with the assurance task. And so when we thought about how do we go about assuring assets with these robotics and autonomous systems using those kind of sources of data, we thought hard about, the importance of being able to aggregate and interpret that data. That's a very important thing. Who owns that data? And actually that's an issue, because people who have data that shows their asset when it fails are reluctant to share that for very good reasons, very often commercial, but to do with safety as well. But it could be in the public interest to do that, right? Because safety could be enhanced as a result. And if you're going to aggregate, interpret, own data, and share it, then you have to have standards for that. And there's still space for standards to emerge to do that. And in the self-certification and insurance, I think this was a very interesting idea that came out, was that if you've got smart software, then you can build systems that can self-certify. They can, to some level, they can monitor their own health. And that has quite a profound effect on how the assurance and the insurance industry are going to work, because it means that not all the certification and the assurance is done as a kind of batch process, at a periodic interval that's dictated by some statistical criteria. You can do a lot more of it only as necessary based on the self-certification that the system's doing in real time. But set against that if you put smart software in there to do that, robotics autonomous systems to do that, they themselves have to be certified. So there's no point in putting in a system that's less well certified than the asset that you're dealing with, because if you do, then it'll be the limiting factor in the overall assurance. So there's a thing you have to think about there, about how you introduce the system. And when we thought about the software systems integrity management, we recognized that there are lots of challenges in doing, safe software, and there's people out there doing that at the moment, and there's lots of expertise. But we recognized that when it came to RAS, the cybersecurity angle and hacking hasn't really been connected onto the community of people who are looking at that for banks and those sorts of applications, are not really working alongside the robotics community. And it is an issue. How do you make sure your drone doesn't get hacked by somebody else over the internet and taken over? So there's work to do there. That's one of our white spaces. And looking at distributed ledger technology, which is another kind of sort of safe, secure, not blockchain. I've been told not to call it blockchain because that's just Bitcoin. But that notion of having transactions properly and correctly recorded, guaranteed, we think is very important for looking at, well, what did the robot do when it was out there, and what commands did it get, and what commands did it issue? I talked about the different kinds of autonomy already. How am I doing for time? No, I'm not on my 2 minutes yet, am I? No. 8 minutes, great. Okay, so I've got more to go. Okay, so designing safe robots and autonomy into systems. So we thought a little bit about how are we going to do that. There's the business of building these systems so they're safe. And clearly the safety must be by design. But there are some issues with that, and also to do, make sure I get these the right way around, that our robots are working in environments that are uncertain and unknown. So if you think of the example of the autonomous inspection vehicle there, it goes off and it swims into the oil field. It swims around, it does its inspection thing. It has a set of diagrams and drawings in its brain about where to go and what to do. But and they may even be the as-built drawings and diagrams, but they probably aren't right. And so, because the place has been, the asset has been modified by various maintenance tasks over the years. So the robot has to map and operate in a world that's uncertain. So even though it's been completely properly certified and it's safe to some level, to some definition, the environment that it works in may not be, or maybe changing. And so you have to think about, well, how do I certify a system that can work in an environment that we don't completely know and can't completely define? And that's an open question, I think, in how we design safety into our robotics and autonomous systems. And there's a big piece about operators. I'm going to come back to this slide here because I remember now why I put it in. I talked about teleoperation, shared autonomy, and persistent autonomy. Persistent autonomy, the operator's put his feet up and he's relaxing and reading the newspaper because the robot's doing it all, right? Not true, of course. But there is an issue, and it comes with self-driving cars, actually. If you suppose the robot gets to a situation where it doesn't know what to do, the standard narrative is that the robot should hand control back to the operator. That's okay, provided the operator is paying attention, right? But if, as in the persistent autonomy case, the operator is busy doing something else, then actually it's the worst thing in the world to hand it back to the operator, because the operator will probably make a bad decision, because the operator is not properly situated with what the robot's doing. And if you look at lots of the examples of these systems that fail, it's in the interface to the operator. There's the Air France crash off the east coast of South America in 2009, I think it was. Basically, the pilots didn't understand what the aeroplane thought was going on, and they spent the whole time trying to fight it, to disable systems, and it's a long story, but it boils down to the pilots and the plane weren't in the same place. The plane was right. I think the pilots were wrong, and it's human error. And so, what to do about that? How should you if you have even shared autonomy, then the operator still is situated with the robot, and because it's doing the operator's doing the cognitive piece, the robot's doing the controlling and sensing piece. In persistent autonomy, if you hand in the self-driving car, if it just hands control back to the operator, then they'll probably do the wrong thing. So that's an issue, and how we deal with that has to be thought about and developed. There are issues about data and knowledge privacy and integrity guidelines, so that we make good use of our RAS data and knowledge that we need to think about. And the privacy issue, I was half joking when I talked about, I'm sure Dyson don't have data going back to their headquarters, right? But you get the point. And what should you do about that? Should you regulate every drone that has a camera on it? You can't own or operate a drone with a camera unless you have a license. Is that going to work? Or is that regulation going to become something that gets in the way of the adoption of the drone for whatever the applications are? And those are things that need to be thought about in order to move forward. And we'd also, just to the earlier point about the robot, which has been assured and is safe, but works in a changing world, one of the things that's coming out of AI, artificial intelligence, is systems that learn. So we can build systems that learn. We can put AI onto robots, and they can learn how to do things. They can learn how to understand things in data. They can also learn sort of indirectly things about the behavior of other things they observe to then predict what they're going to do next. And in all those learning applications, how do you make sure that the robot learns the right stuff and not the wrong stuff? There were some examples in the discussions I recall about learning from Facebook, which isn't quite the right domain. But it highlighted that there's lots of things you can learn from Facebook, right? But they might not be the right sort of things that you want a system of any sort to learn. So again, we need to think about that and how to do that. And how do we certify a system that learns? If it's going to adapt what it does and how it behaves based on the environment that it's in, and it's not been predefined, then that kind of goes against the whole grain of what assurance is all about, where you have a specification, it's supposed to do this, and you make it do it, and you guarantee that happens to some level. So there's some deep thought needed about that, and about how much learning should you put on a robot in order that, given that it has to work to a certain level of assurance and certification. And there's a lot of human, moral, and ethical factors that then go into the sort of decision-making that RAS are involved with. The classical one that everyone always talks about is the car, and the car's driving along, and it's going to crash, and you've got the president and the baby, which is the one that you should hit. And I guess it depends who the president is, based on recent events in North America. And future events, actually. But you understand, we say, but there are, and if you don't think about this, then the people who will decide that are the engineers, right? Now, engineers are wonderful people, but they may not make the right ethical choices in these things. And we do need ethical guidelines to think about how to do this kind of stuff. And it's something that the public have to contribute to. It's not just something that, a mixture of people in well, it used to be a smoke-filled room, but we don't do that anymore, should do. So those are things that need thoughts. And so building public trust is something that we need to do. And I think there's no doubt that there's the sorts of trials that are going on in Milton Keynes and Greenwich with the self-driving cars. These are great because people are getting to see the robots, see the systems being used, and there's nothing like seeing them and working with them to then build that trust. But people also have to believe that the companies that are manufacturing this stuff are actually ethical in the way, we don't always believe that some of the large multinationals, we don't always believe that they behave ethically, but we don't know, of course, it's all rumor. But we need to try and develop that with the robotics companies as they develop. And have a narrative which isn't just about, the loss of jobs and growth and that sort of alarmist piece, which is the way it's been driven largely in the public at the moment. And there's a skills piece that we've put in there, and that I think comes probably with every review. There's certainly a lot of STEM work to do in the schools, supporting the primary school teachers actually, we've done a little bit of this, and putting robots into primary schools with the kids age 8, 9, 10. And it's very successful, provided you give them the right support in terms of equipment and demonstration videos and so on. There's a lot of that kind of stuff. There's a lot of training and skills of PhD students and people who've got the software skills and the algorithmic skills. And there's even retraining of the people who, for those who are displaced and have their jobs, how do you upskill? It's not displacing them, but it's how do you upskill people so that they can still be beneficiaries. So there's a lot of work there. And I'm not going to go through it here, but we did a lot of thinking about what are the impacts and applications and some of the scientific underpinnings. Again, you can't read them here. Certainly, there's some interesting developments in the long term, quantum computing and so on. But there's things like synthetic biology is starting to come together with robotics, and we can imagine 3D printing biological organisms, in 15, 20 years' time, that themselves will become biological robots. So think about what the ethical implications of that are going to be and how the Twitter storm will go with that kind of thing. So here are the 4 categories of our findings and recommendations. There's 2 or 3 on openness and sharing on the left-hand side there. So we need to go think about open data standards. We need to think about open data sets, and we need to think about how do we share the knowledge and the data, dealing with all these issues of privacy on the one hand versus public good on the other. And that's not new, that's a sort of general big data issue, but it's particularly relevant to RAS because RAS are things that act in the environment. There's things to do on assurance and certification. So, how can I build assets that self-certify? And what are the issues in that? And one of the nice things about that, although it's quite a high-level ambition, in order to do that, it involves quite a lot of deep technology stuff in order to do it. So it's back to engineering again, which for me anyways, is good. So, we have to be able to do fault detection and diagnosis and prognostics and all those kind of things on our assets in a much better way than we do at the moment. And be much more joined up about how we use data in smart spaces in some of these assets. And how do we do this assurance piece about learning systems? With a system that can change what it knows, how it behaves, the logic of what it does as it adapts. How do I assure that? There's the security and resilience piece. So the cybersecurity point that I made, we need to make sure that all those techniques that are being developed for cybersecurity, for protecting computers from being hacked, we have those installed in our RAS so that they are protected. And the whole thing about software systems integrity, that we build the integrity in a way that's cost effective, because you can do it, but it's very expensive. So can we be leaner in the way that we do that? And can we do it in a way where all the processing power on the robot isn't being used to keep all the integrity systems going and all the encoding and so on, rather than carrying out its desired function. And then finally, sort of public trust, understanding, and skills. We do need to go and work on some of these ethical and trusted frameworks. We need to have multidisciplinary groups of people coming together again to actually map out what these frameworks should be, answer those questions, so that when engineers come to design systems and when we come to do standards and to do policy work, and we have something to go on where there's a general consensus, this is the right ethical approach to building these systems. And then skills. There's a variety of activities in skills, as we've said. So that's it. I'd like to thank everybody who's been involved in that Foresight review, David in particular for helping get it over the line 2 a.m. and actually Ruth at 2 a.m. as well with doing the final edits. She's great. Those who've been where I am will know that she's great at crafting words. And there comes a point where you can't see the wood for the trees, and Ruth did a fantastic job helping us to get that over the line and was very patient with us when we were very busy. So that was great. So thank you very much, and it's been a great pleasure.
So we have time. We'll take 2 questions.
I would like to ask the question or raise the question around ethics and the human-centered automation with respect to persistent autonomy. Do you think there is a missing piece around philosophy for these robots or autonomous systems, like whether we do bring these technologies without a purpose, like because it's existing and the technology is there? Do you think that there is lack of direction from a philosophical side, what these robots are brought into the world for?
Mm-hmm. Yeah, that's a great question. I ask that about the people doing humanoid research all the time, because we're nowhere near producing humanoids that can do useful work. Those, I mean, I could show you some great examples of them going wrong, falling over, and and yeah, they consume too much energy. They break easily. So and there's always an easier way to do it than with a humanoid, right? Now, one day in the future, we might get there, right? So you might argue there's no purpose in doing humanoids, but the students love it. When the students come to the Centre for Doctoral Training, they all want to work on humanoids, right? Because it's fun. And I think it's a bit like kind of going to the moon. We went to the moon and got non-stick frying pans. So by working on humanoids, we advance a lot of algorithmic stuff that can then get used for other things. Certainly, there are real drivers around productivity and safety that are economic and health, which are the reason these are being adopted. So, yeah.
Here, one last question.
Thank you very much for sharing this. It sounds that it's quite software-centric of what you're describing, and I understand it makes sense because that's where the immediate impact is coming from. But it's shocking that these devices, although they've been so powerful, they've evolved so much, still we're running Siri on the cloud, and we're not able to run this locally. And there's clearly a need for the hardware that is capable of running advanced machine learning, implementations like supervised and supervised learning and extrapolating patterns. I mean, what's your view on that?
There's some truth in that. We're just about to spend £120,000 on a machine learning box full of GPUs that does exactly that. And it's big and it's hot, and that's the reason why Siri's in the cloud, right? Because you can't get it onto a form factor at the moment that will fit on your iPhone. There's another reason for being in the cloud, and it's this aggregation of data. So Siri works because all the queries and questions and accents that we have, they all end up in one place, and the data is aggregated and used, and the machine learning works on all that. So you get a better performance and a better service from Siri because of that aggregation into the cloud. So the reasons for that are both technological and functional, I think. And it's interesting, Moore's law, that computing power doubles every 18 months or whatever it is. Actually, there's another statistic which says the number of people predicting the end of Moore's law doubles every 18 months. Right? But and those of you with bank accounts that have compound interest, it's interesting after some period of time when doubling really means something, right? And we're at that stage now. The reason AI is taken off again is partly because it's been doubling, and so we can start doing stuff that we couldn't do before. It's not clear that it's going to continue doubling because the economics of going down to the next micron level, for Intel on the chip design are such that it's going to cost them. They won't get the money back. It's going to cost them too much in the amount of power, the places they have to put the rivers that they have to use to get the power to do the wafer fab. And so for Moore's law to continue, there is a school of thought that says it's got to happen through greater efficiency in software and other kinds of changes in the hardware design, which are possible. Right, but that will only go so far, and that's why there's an interest in things like quantum computing coming through, because you need new paradigms. So, how long it continues, is we have to wait and see. Yeah.
Thank you again, David.
Yeah.